Welcome back to module 15. We are continuing ab initio molecular dynamics, discussion on ab initio molecular dynamics, which is relevant to ultrafast processes. We are primarily interested in the dynamics associated with photophysics and photochemistry. What we have discussed so far is mixed quantum classical approach. In mixed quantum classical approach, we propagate nuclei with the help of classical propagator, which is nothing but Newton's second law, but we take the potential which provides the force acting on the nucleus. We get the potential from electronic structure theory calculations. And in the problem of photophysics and photochemistry, we have seen that we have to express electronic wave function in terms of Cassius wave function. That is one way of thinking of it, and we have shown here the hierarchy of the Cassius wave function. Cassius wave function is the electronic wave function, the expression of the electronic wave function. But the total wave function, we have seen that total wave function is nothing but the summation of nuclear product of nuclear wave function and electronic wave function. So electronic wave function we know how to represent. This has to be represented with the help of Cassius methodology. But how do we express this nuclear wave function? That is an important question right now. So our next question is that how do we express time dependent nuclear function in terms of basis set? That's called basis set approach to QMD, quantum molecular dynamics. What kind of basis set would be suitable to represent nucleus? The kind of basis set which we have used in expressing electronic wave function is that atomic orbitals, which is nothing but a basis set represented by the basis set, and many basis sets which are available. 631G basis set is one of the commonly used basis set to express electronic wave function. But question is, how do we express nuclear wave function in terms of basis set? To understand that, we will first look at the harmonic oscillator. Atoms are not classical point particle. For any classical point particle, both position and momentum can be exactly determined at any point of time. Quite on the contrary, atoms are quantum mechanical particles, for which position and momentum cannot be precisely known simultaneously. This is a consequence of the Heisenberg's uncertainty principle. A quantum mechanical particle is described by a wave function. Under the simple harmonic oscillator approximation, vibrational wave function for a simple diatomic molecule has a width. So let's say I have a diatomic molecule, and the way we express diatomic molecule is that one atom is anchored on this axis, on this y-axis. It will be anchored. It will not move along this way or this way. It will not move along this way. It will only move along the y-axis, and another atom will be moving along this direction, either this way or this way. So this is the diatomic molecule. So this x-axis is representing the internuclear distance. Under the simple harmonic oscillator approximation, vibrational wave function for a simple diatomic molecule has a width. So what does it mean? Even if I am in the zeroth energy level, this dotted line is representing the zeroth energy level of the vibration. The nucleus is like this, and its internuclear distance is r0, which is that equilibrium distance. We call it equilibrium distance. But there is if we say that this atom is anchored on the y-axis, which is the potential energy surface axis, potential energy axis, on this axis, if it is anchored here, then it is anchored at this r value, r equals certain value, let's say r1, then this position will change. So at this position it is r equals r0, and it can change. The position of this nuclei will change as it's vibrating. So when it's vibrating, it is quite clear that even at the zeroth energy level, there is an uncertainty of the position. So this width of the vibration this width of the vibrational wave function represents the position uncertainty of the atom. The ground vibrational wave function under simple harmonic oscillator approximation represents a Gaussian wave function. Center of the Gaussian represents the classical position of the atom. These are the very well-known facts from preliminary quantum mechanics. For the sake of simplicity, we can consider one-dimensional problem here. We can assume a Gaussian representing the vibrating atom. Center of the Gaussian represents classical position of the atom, but we note that this function does not represent a traveling function. So what we can do is that one can say that, okay, I have to express this wave function, nuclear wave function. So I will consider the ith nuclei, which is here, ith nuclear I can express like this way. I can say that it is nothing but a Gaussian function, ax square, and a is related to its width. This width is related to a. This width is related to a. So I can use a Gaussian function to represent Gaussian basis to represent the nuclear position. But the problem is that if we represent it, then we know that the Gaussian function, this is not a propagating function. This is not a propagating function. This is always centered at x equals 0. So for the given problem, one can rewrite this expression as minus a r minus r naught whole square. Then it is centered at r equals r naught, and we have seen this in our previous lectures that we had a Gaussian pulse, and if the Gaussian pulse has to be centered at r equals r naught, then we know that this is going to be the expression. But this expression doesn't indicate that this function will move along a particular direction. In order to get something moving or propagating, we know that we have previously expressed our ultrafast pulse as follows. The expression for ultrafast pulse was Et equals At multiplied by I omega average T minus K average Z. So that was the expression, and we said that this envelope function can be expressed as some kind of Gaussian function minus a t square. In the time domain we are representing, that's why t square e to the power I omega average t minus k average z. So this was the expression we used. So what was quite clear that this envelope function is propagating because of this additional term. So this term is representing a propagating wave or propagating component. So in the space domain, if we want to express it as a propagating traveling wave, then what we need to do is that e to the power minus a r minus r naught whole square, this is a Gaussian function, then it has to be multiplied by e to the power I k z. If we multiply by e to the power I k z, then this is an expression which is showing that it is a traveling Gaussian. Nuclei should move. Center of the Gaussian is going to be the classical position of the nucleus, and it can move. It can move because this is representing the Gaussian function, and this is indicating that this part is indicating that it will be propagating along the z direction with the k vector. Now question is, for a nucleus, it is a nucleus, it is not a, it is a point part, it is a particle, and we know that for any k, this k can be expressed as 2 pi by lambda. for any k. And we know that we are dealing with nucleus, and that's why we have to deal with the particle wave or de Broglie matter wave, which can be expressed as lambda equals h by p, where p is the momentum. Thus, wave vector in momentum space can be given as k equals 2 pi p by h, or in other words p by h by 2 pi, which is giving me reduced Planck constant, and in atomic unit then k becomes p because h cut is 1, is taken to be 1 in atomic unit. So k is nothing but p. So I can rewrite this expression as follows. I can then express the traveling Gaussian function as follows. It is going to be e to the power minus a r minus r naught square representing the Gaussian, and the traveling part is going to be, this wave component is going to be I, then p and x. P and z will consider as r minus r naught. The z is nothing but the distance, and that can be represented by this. So final expression for a traveling Gaussian for a particular nuclei is going to be this. The first part, the first component, this is representing the Gaussian part, and this is representing the propagating wave part, matter wave part. Now, if we have this kind of expression, or one can express for simplicity, one can keep this form as well, e to the power minus a x square multiplied by e to the power I p x. If it is z, you can express in terms of z as well, that's not a problem. We are just expressing in terms of x. So this is the expression for a traveling Gaussian. And each nuclei, ith nuclei, can be expressed in terms of traveling Gaussian. So this A should have a subscript I, and P should have a subscript I as well, because it is associated with ith nuclei. So we can definitely normalize this kind of function. So we are taking a nuclear wave function as in this form, e to the power minus a x square e to the power I p x. So we can take the magnitude, which is nothing but this, and which we get it a square e to the power minus 2 a x square, and this is magnitude square, and what we get is that now we'll do the normalization, and for normalization we'll take minus infinity to plus infinity integration over dx, which we get to be 1, minus infinity to plus infinity dx, and we get the integration to be 1 if it is a normalized function, and this gives me a square, and this integration we get from a standard integral, Gaussian integral, we get 2 pi by 2a, which is 1, or a equals 2a by pi, square root of 2a by pi, and this is not going to be square root. A is going to be 2a by pi to the power 1 by 4, and so the normalized one dimensional, so one can write down normalized traveling one dimensional Gaussian, we can write like this, is nothing but 2a by pi to the power 1 by 4 e to the power minus a x square e to the power I px. So that's the expression for the nuclear, one nucleus, normalized traveling, which the nucleus has been expressed in terms of normalized traveling one-dimensional Gaussian. Now, if we have n number of system, let's say, and then I have 3n number of total degrees of freedom, I'll have, and because each atom can move along x, y and z direction, if the system with n atoms needs to be represented by traveling Gaussians, one can take product of one-dimensional Gaussians. Each dimension is represented by r and rho represents the 3n Cartesian coordinates. So what we need to do is that we have to use a localized Gaussian. That's why we are taking a product. So the product has to be is a product of 3n number of one-dimensional Gaussian. Each Gaussian is represented by its A, which is and this is a normalization constant, and its exponential part having this a r square. This part is the Gaussian part and this part is the propagating wave part, which is the similar expression we have seen. Here we have changed the variable from x to r representing either x, y or z component. So how many such r we have? We have 3n number of such r we have, and r is representing the general variable along this particular direction. We note that different width, that is the a rho, and different momentum has been assigned to each one-dimensional traveling Gaussian. So if I have 3n number of degrees of freedom, then we should have 3n number of this one-dimensional Gaussian, propagating Gaussian, and we should take the product of each Gaussian to represent the nuclear wave function. To develop a basic understanding, instead of n atoms, one can stick to one atom for the time being, and one can also assume the one-dimensional problem. We have no electrons, and we can also assume that we have no electrons as well. We are just trying to play with the nuclear wave function. Nuclear wave function will depend on space and time x and t, which can be expressed as a linear combination of many trajectories, and is something like that. So many trajectory, what does it mean? It means that I can have a trajectory like each trajectory is represented by one-dimensional traveling Gaussian. So I will consider this chi is nothing but one-dimensional traveling Gaussian. We do not have any product of different Gaussian because we have only single atom and one dimension. Under this approximation, one can express the total nuclear wave function in the basis of traveling Gaussian, and one can say that this individual traveling Gaussian is not time dependent, but its expansion coefficient is time dependent. So if we have this situation, then what we are going to do here, also we are not considering any electron. We do not have any electrons, so we do not have electronic wave function. It's just an assumption. Under this assumption, we'll try to understand what is going on if we plug that into the time dependence Schrodinger equation. Time dependence Schrodinger equation reads like this, which is the total wave function. Now here total wave function will consider that chi, that is xt, equals h chi, that is xt. This is my total wave function. So I'll insert that one. I have considered that no electrons are there, so that's why no electronic wave function I have included. I have just included the nuclear wave function. So if I have this situation, then I can plug that in here, and what I can write is that I partial derivative with respect to t summation of c j, that is the index as a function of t, then that is the j, that is expression like this, and equals, this is h summation of cj t, this is j, then chi j x. We have assumed that this traveling Gaussian function or trajectory is not time dependent. In our next derivation, we will consider it to be time dependent, but in this derivation we are not considering it to be time dependent. So if we have that, then we can do this time derivative, and we can write down this expression as j. This is going to be then cj dot, dot is expressing the time derivative with respect to time, then ijx equals, this is going to be nothing but cj t, then h, then jx. Now in quantum mechanics, often we use we make use of orthonormalization condition. However, it is not necessary here that these Gaussian functions are orthonormal, but we can still multiply by this chi I from the left hand side. So I can rewrite this expression as cj, that is the dot time derivative, then integration is going to be I j x, both are function of x, equals summation of j cj t, then chi I x h chi j x. So we can write this, and this expression can be simply written as summation of cj, the first derivative, then this integral will write down s I j equals minus I summation of cj t, and this integral will call it hij. Considering now three bases, one can then, I'll write down this expression one more time. We have written cj t, its first derivative, then sij equals minus I summation of cj t hij. That is the expression we have. Now if I consider three bases, then one can write down C1 T, which means J will be 1, 2, 3. So J is going to be 1, 2, 3. In that case, one can write down C1 T S11 plus C2 T S12 plus C3T S13 equals minus I C1T H11 plus C2 H12 plus C3. I'm not writing as a function of time for these coefficients, just to quickly express it. 1 3. So this is one equation we get, and then one can write down one can write down, this is I equals 1, then I equals 2, and I equals 3 I have to write. And for I equals 2 I can write down C1 S21 plus C2 S22 plus C3 S23 equals minus I C1 H21 plus C2 H22 plus C3 H23. And again I equals 3, I can write down C1 S31 plus C2 S32 plus C3 S33 equals minus I C1 H31 plus C2 H32 plus C3 H33. So this can be, these three equations can be expressed in the matrix form. And how do I express in the matrix form? I can express it in matrix form S11 S12 S13 S21 S22 S23 S31 S32 S33 is multiplied by C1 dot, C2 dot, and C3 dot equals minus I of H11 H12 H13, then H21 H22 H23, then H31 H32 H33, then C1 C2 C3, which can be rewritten as, in the matrix form can be rewritten as this. So this is suggesting this part, this matrix is we have taken here, and this matrix is here, and this coefficient is here. So we can rewrite, we can rewrite this one as in this matrix form. So finally what we are getting is that a value for dc dt. And why we need this value for dc dt? Because we if we want to propagate it for a particular state, what is the population that will be controlled by dc dt. So if we find out, if we want to know t plus delta t, after time t plus delta t, what is the coefficient c, what trajectories exist, and what trajectory population we should consider, that's going to be c at t naught plus dc dt at t naught multiplied by delta t, if the delta t is very very small. This is the up to first derivative we are expanding Taylor series expansion. So this dc dt one can get it from time dependent Schrodinger equation, because the first initial coefficient is known for a particular expansion, next onwards in time it's unknown, and that unknown coefficient can be calculated directly from the from this time derivative. So in this expression, in this derivation, what we have considered time independent basis. Now we can consider time dependent basis, and if we consider time dependent basis, then again we have to plug that into the time dependent Schrodinger equation, which is the partial derivative of chi equals h chi, and it is nothing but I del t summation of c j then chi, which is now a function of x and t. That's the way we are taking, and in that case h is going to be summation of cj then chi, it is now function of x, it is a function of now x and t. So we'll get additional terms, because now one can write down that this is nothing but summation of cj dot multiplied by this function plus, I have to also consider the other derivative which was not present in the previous expression. This is going to be cj and the first derivative of this one equals now summation of cj then h then nuclear basis set, this one, which can be rewritten as I summation of, now following the previous procedure we can multiply by this, this is going to be j actually. So there is an index j here, there is an index j here, there is index j here, index j here. So this we previously have seen, we have multiplied by chi I like this way, so we can do the same thing now. We can multiply with this chi I, and then this is chi j plus I cj then chi I first derivative of chi j equals summation of cj then this is chi I h chi j. So this is the expression we finally get. So we know that this is, we are going to write down, so this whole expression can be reduced in the well-known form, that is the cj dot then this is sij plus I. Here we remind that this I is not the index I here, this is an index I, and this is nothing but the complex number square root of -1. So I this can be written as cj, then this is, we are saying sij dot, sij dot, this expression is sij dot, which is nothing but minus I, sorry, not minus I, we still have this summation cj, then this is called hij. Now I can take this I from here and place it on the right hand side by minus I, and then one can write down this expression as cj dot sij equals minus I summation of hij minus isij dot then cj. This is the way one can express. So final expression for the time dependent coefficient we get like this. In the previous expression we didn't have this term, but now we have additional this term, and if we take now again 3 bases, then one can write down like following way. We can rewrite that expression again here for us to remember. That is the Cj dot T Sij equals minus I summation of Hij minus I Sij dot then Cj. That was the expression. So taking again 3 bases, one can consider I equals 1, I equals 2 and I equals 3. If I consider that, then what I get is that I get C1 dot S11 plus C2 dot S12 plus C3 dot S13 equals minus I C1 H11 minus I S11 plus C2 multiplied by H12 minus I S12, these are dots, plus C3 into H13 minus I S13 dot. This is the expression we get for the first one, I equals 1, then I equals 2. The procedure is exactly the same procedure. We are following the same procedure which we have followed previously. This is going to be S21 plus C2 dot S22 plus C3 dot S23 equals minus I into C1 H21 minus I S21 dot plus C2 H22 minus I S22 dot plus C3 H23 minus I S23 dot. Similarly, for I equals 3, I get C1 dot S31 plus C2 dot S32 plus C3 dot S33 equals minus I into C1 H31 minus I S31 plus C2 into H32 minus I S32 dot plus C3 into H33 minus I S33 dot. So these are the expressions we get. Finally, in the matrix form, if we want to express, one can do it S11, S12, S13, S21, S22, S23, S31, S32, S33, C1 dot, C2 dot, C3 dot equals minus I H11 minus I S11, H12 minus I S, these are dots, 12 dot, H13 minus I S13 dot. This is an expression, then multiplied by C1, C2, C3, and the second term here H21 minus IS21, H22 minus IS22, H23 minus IS23, H31 minus IS31, H32 minus IS32, H33 minus IS33. So these are the expressions we get. So finally, the matrix form can be represented by this equation where the first derivative of this coefficient can be expressed as follows. Here, this is the inverse matrix, this is the Hamiltonian, this is the matrix represented by this, and this is represented by this. So we get, and this is here. So we can express like this way. Two different kind of equations we get, and what we see here, we should remind ourselves that this Sij, this Sij is like an overlap matrix. This Sij is like an overlap matrix, is nothing but chi I then chi j, but Sij dot is not d dt of chi, the time derivative of the overlap matrix. It is not like this, rather it is, as we have defined before, it is chi I then the first derivative of chi, sorry, this is chi j, this is the expression, and then H, this is something which we should remember. So S dot here is not the time derivative of the overlap matrix. We'll stop here and we'll continue the discussion of quantum molecular dynamics, which is important in to understand ultrafast processes, and we'll continue the discussion on the Gaussian basis to express the nuclear wave function. We'll meet again for the next lecture.